boys, and welcome to the first annual Fluid Flow Olympics. You're in for a great matchup today between the liquids and the gases. And for my first guest today, we have the liquids coach, Dewey Drop.
Yeah, Mr. Ray, what's up? What's more? Yeah, there you go.
Hi, Dewey.
Hey, Flo, how are you doing today?
I'm good. How do you think your team is going to do today in the races?
Oh, I am pumped. I think we're going to do awesome today. We can adapt to any race environment, and we take the shape of any container we're in. We have this dominated. And my molecules and I, we're really close, we're really tight-knit, so that'll be a great advantage. And we definitely handle pressure a lot better than gases, so you better watch out.
Thanks for your contributions, Dewey, and we hope to see your team do really well today in the races.
Thank you, Flo. I hope so, too. Yeah, make it rain!
Woo! And for my next guest, we have the gases coach, Sky Viento. Hi, Sky. How are you?
I'm good. How are you?
Good. How do you think your teams are going to do today in the races?
I think they're going to do really well. Our molecules may not be as close together as the liquids, but I'm sure that we can really go the distance. Our densities may change with the pressure, but that's only going to make us do better.
Liquids coach Dewey Drop has been quoted as saying that he's going to precipitate all over y'all. What do you have to say in response to that?
I have one thing to say. I'm going to blow you up.
All right. Thanks, Sky, for your commentary, and we look forward to seeing your team during the races.
You're welcome. Thank you so much.
And now it's time to see how hard our teams have trained to get ready for this year's Flow Olympics. The liquid molecules are training to stay in the shape of a small container. Wow, they're going to be hard to beat, Dewey.
Yeah, we are. We've been training hard this whole water cycle. I think we got this.
Uh-oh, they might be a little too close for comfort.
No way. They know what they're doing. They've been living in clouds and they can handle it.
Now on to the gases training. Look at these daring gas molecules. No container can hold them back, can it, Sky?
You sure got it right. We can't even train outdoors because they'll just float away. Plus, they don't run into each other like some of those liquid molecules do.
I wonder how both these teams will handle the changing environments. Uh-oh, looks like it's getting a little cold in there. I don't think they're going to move very fast in that environment.
You can slow us down, but you'll never stop us.
I agree. Slow and steady wins the race.
Oh, and now things are heating up in there. Look at that speed and agility.
Oh yeah, and we're just warming up. We're not even close to our boiling point.
But remember, gases can always take the heat.
Now that we've seen how hard the teams have trained, it's time to kick off the Flow Olympics with our theme song by Eddy Currents and the Turbulence.
We live the life of a physics student, and we're here to tell you studying would be prudent. You got a test tomorrow? Hey now, don't panic. We're here to teach you all about fluid mechanics. The two types of fluids are liquids and gases. To find their densities, you need to find their masses. Fluids follow laws, you cannot bribe them, and we are here today so we can describe them. All fluids move faster when they get hot, but liquids have definite volumes, gases do not. So liquids take the shape of their container. How can we make this stuff any plainer? There is a kind of fluid that's called ideal. It's used for calculations, though it is not real. Like me, these fluids have a wicked steady flow, and they're not turbulent or viscous, just so you know. In the water, there's this thing called buoyant force. It's the upward force exerted on objects, of course. Buoyant force is the weight of the fluid displaced. Learn this now, and your test is sure to be aced. You need some formulas to help you measure. One is force over area is equal to pressure. Hope you don't mind that we're being so factual. Now you're going to learn about Pascal's principle. In a container, if pressure increases against a wall, it increases everywhere according to Pascal. There are more principles, as you will see, like the one made by Bernoulli. He said fluid pressure goes down as it gets faster. Yeah, he was pretty much the fluid master. Turns out this is the reason airplanes fly. Hold on a second and we'll tell you why. It's like when you blow across the top of a paper sheet, it rises instead of falls. Hey look, that's neat. The speed on top goes up so the pressure goes down so the object can rise and fly above the town. I mean, I guess you could say fluids are pretty chill. And all these facts sure gave us quite a thrill. We hope you learned a lot about fluid mechanics. Now get ready for the Fluid Flow Olympics. Yeah!
Hi, it's mathematician Daniel Bernoulli. Hi, Mr. Bernoulli. How are you?
Hi Flo, I'm doing well, thanks. How are you today?
I'm good. Mr. Bernoulli published a book containing the world-famous Bernoulli's principle, which is very important to the world of fluid mechanics. Can you tell me a little bit more about your principle?
Yeah, I'd love to, Flo. My principle states that as the velocity of a fluid increases, its pressure decreases, and this is the reason why airplanes fly. And it relates to the conservation of energy because as the velocity of a fluid increases, the kinetic energy also increases, so the potential energy goes down, and that's how it's all conserved. It's always equal. Conserved.
Thank you, Mr. Bernoulli. Your discoveries really influenced the world of fluid mechanics. Now we have a special presentation by the gases showing us how this principle works.
This race has a lot to do with Bernoulli's principle. When the balloon begins to move out of the low-pressure stream, the high pressure of the air in the room pushes it back into the moving stream. When you tilt the nozzle, the pressure of the room is still high enough to push the balloon back into the airstream, even if the moving stream is at an angle. However, at a large tilt, the force of gravity is greater than the force of the air pressure holding the balloon in the stream, and the balloon will fall.
Here with me now is world-acclaimed physicist Sir Isaac Newton. Hi, Mr. Newton. How are you?
I'm good. I'm ready to get down to business.
Can you explain to me your discoveries regarding fluids?
Sure. First off, viscosity is very important because it's the measure of the resistance of a fluid. Non-Newtonian fluids have a high viscosity, and when stirred, a hole is left behind, and that hole gradually fills up. On the other hand, a Newtonian fluid has a low viscosity, and the fluid continues to flow regardless of the forces acting on it. So, for example, a Newtonian fluid is water.
Thanks, Mr. Newton. And now we have a presentation by the liquids showing us what happens when you apply pressure to a non-Newtonian fluid. This experiment will show a non-Newtonian fluid made by mixing cornstarch and water. As you can see here, when not much pressure is being applied on the mixture, it flows and behaves like a normal fluid. However, because of its high viscosity, the mixture acts like a solid when a lot of pressure is put on it in a short amount of time. Because of this, it is possible to punch or hit the mixture without getting anything on your hands. But, as you are about to see, if you apply pressure over a long time rather than in a quick burst, the mixture will behave as a fluid. In this race, water is boiling in a flask that is covered with a balloon. As the water boils and is turned into steam, the molecules begin to move faster and faster. As you can see, when the molecules move faster, they try and escape the flask and instead move into the balloon. When this happens, it causes the balloon to fill with air, as you can see happening here. And as you can see, as more and more water vapor escapes from the flask, the balloon gets fuller and fuller. In this race, water is being boiled in a soda can. As the water boils, it changes from a liquid to a gas, and you can see the gas escaping from the can here. This gas, or water vapor, pushes the air that was inside the can out into the atmosphere. When this can is quickly put into cold water, the water vapor condenses into liquid, and because the liquid can't put as much pressure on the walls of the can as the water vapor did, the air pressure outside the can can now crush it. In this race, the liquids will demonstrate that pressure increases with depth. A PVC pipe with 4 plugged holes is filled to the top with water. When all 4 holes are unplugged at the same time, you can see that almost no water comes out the top hole, but a lot of water comes rushing out of the bottom hole. This is because there is more pressure at the bottom of the tube than at the top of the tube. Now it's time to announce the winner of the Flow Olympics. Dewey, how do you think the liquids performed today?
Flo, we hit some turbulent, rough patches, but we got through all those obstacles and we got back into the streamlined, laminar team that we all know and love.
What do you think your team has taught us today?
I think we showed that, like non-Newtonian fluids, you really have to stay solid against strong forces, and you have to have a high internal viscosity to resist the friction within yourself and resist change. I think we really made Newton proud of that. And also in the PVC challenge, we also showed that when the pressure increases, you have so does the depth. So we really had to dig deep down within ourselves to succeed. And overall, we proved that what doesn't spill you makes you stronger.
Thanks, Dewey. Sky, what do you think your team has taught us?
Well, we showed how planes fly through Bernoulli's principle, and I'm pretty confident that we rose above the competition. We definitely displayed some good sportsmanship when we worked with the liquids to blow up the balloon. As the liquids heated up, the gases took over, and we successfully inflated the balloon. I'm proud to say we stayed true to ourselves and were able to cover a lot of ground and weren't limited by the shape of our container.
Thanks, Sky. And now for the results. I bet you're all wondering how we come up with the winner. The equation is PV equals NKT. The pressure of players are under times the volume of the vesicle they are in is equal to the number of players times Boltzmann's constant, a number constant from team to team, and the pressure of the fluid. And the result is a tie. Everyone did so great today. You both get the medal. Share.
Nice game, Sky.
Nice game. Congrats to both teams, and thank you for watching the first annual Flow Olympics.